Hello, my name is Kristiane and I will be presenting my Lab 3 black hole. So, the objective of this lab is for us to derive the net force acting on a system based on information of its motion. In this lab specifically, we'll be analyzing the trajectory of a star orbiting a black hole. So, we'll be deriving the net force acting on this star, which would be our system, and we are assuming that the only force acting on the star, which is our system, is gravity. Now, how are we going to do this? We're going to use glow script coding to show the gravitational net force acting on the star, which we will decompose into two components, its parallel and perpendicular force. Using this information, we're going to estimate the mass of the black hole. Why are we trying to compute this? We want to show the relationship between the parallel and perpendicular components of the net force at a specific point in the system's motion. Here we can see a preview of my results. We will soon see why this makes sense. Now let's take a look at the fundamental principles we'll be using in this lab. One is Newton's law of universal gravitation, which we will use to compute the mass of a black hole. Another is the momentum principle, from which we derive the F-net parallel to motion and F-net perpendicular to motion. Finally, we know that the net force acting on our system is the sum of the parallel component of the net force and the perpendicular component. So for the initial conditions of our code, the star's trajectory is keyed to our Georgia Tech email address. So in the first line, I inserted my email. Then we defined the gravitational constant g, the mass of the star, and we calculated delta t because we knew that the time between data points was 1 day. So 24 hours times 60 minutes times 60 seconds, which will give us a day in seconds, which is 86,400 seconds. Now let's take a look at the more complex part of our code. So first of all, we computed the initial and final velocity, which we then used to compute the initial and final momentum, because momentum is just velocity times the mass of the object, in this case the star. Our delta v is our final velocity minus the initial velocity, and our delta p is our final momentum minus the initial momentum. dp/dt is equal to delta p over delta t, and that is our net force. To calculate dp/dt parallel, we first computed the unit vector, which is the initial momentum over the magnitude of the initial momentum. And then we multiplied that by the derivative of the magnitude of the momentum over delta t. Now, to find the perpendicular component of our net force, we know that the total net force is equal to the sum of the parallel and perpendicular components. So, the perpendicular component of our net force is equal to our total net force minus dp/dt parallel. Finally, we calculated the mass of the black hole by using Newton's gravitational law. We isolated for the mass of the black hole, and we got that the net force, the magnitude of the net force, times the magnitude of the position of the star, which is the distance between the star and the black hole squared, over the gravitational constant times the mass of the star. This would give us the mass of the black hole. Finally, we defined each arrow that would represent our net force, the net force in the parallel direction, and the net force in the perpendicular direction. Because each of our forces is so large and our arrows would not fit in our computer model, then we have to put the arrow scale to be a very, very small number to make the arrows a reasonable size. We can see that the orange arrow is the net force, and it's pointing towards the black hole, because we know that the net force is only the gravitational force of the black hole on the star. So this makes sense. Now the pink arrow represents dp/dt perpendicular, which is pointing towards the center of the kissing circle. And finally, the blue arrow is our dp/dt parallel, which points in the direction of the star's trajectory. These are our final results, and they do make sense because if we use the Pythagorean theorem with our F-net parallel and our F-net perpendicular, we do get our total net force. So what does this mean? How is the net force and its parallel and perpendicular components different from the rate of change of momentum and its components? Well, mathematically, they are equal, but the difference is that we can compute dp/dt because we have the star's trajectory in motion, but we cannot directly tell what the net force and its components are since we are not given the mass of the black hole. We are basing the net force and its components on the trajectory of the star's motion. Now, what would happen if we placed a new black hole in the same position as the original one, but the motion of the star remained the same? Could we find a different mass for the new black hole? Because the only force acting on the star is the gravitational force between the star and the black hole, and the motion of the star is identical to the original one, then that means the net force on the star must also be the same. And because the net force depends on the mass of the black hole, then the black hole's mass must remain the same. In conclusion, I noticed that the mass of the black hole fluctuated after every time step because the net force was also changing. This, of course, cannot happen in real life, so we could improve our model to show a more accurate representation of the black hole's mass. A key takeaway of this lab is that if we are given the trajectory or motion of a system using dp/dt parallel and perpendicular to analyze and predict the net force acting on the system can be very accurate. Thank you.